This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome back to Chapter 2 of our series, Shaping the Modern World, Stories of Discovery. In this episode titled Eureka, Moments That Changed History, we'll explore some of the most significant scientific breakthroughs and uncover how these moments of inspiration reshaped our understanding of the world. So, let's dive in. A young clerk shuffling patent paperwork quietly rewrites time. An apple falls in a quiet orchard and pulls the planets with it. In this episode, we'll chase those rare aha flashes when the universe suddenly makes sense, and everything humans build must change. Some breakthroughs don't just solve a puzzle, they change what counts as a puzzle in the first place. Newton and Einstein didn't simply add new answers, they quietly swapped out the questions. Before Newton, motion in the heavens and motion on Earth were filed in separate mental folders. Before Einstein, space and time were treated like the fixed stage on which events unfolded, never actors in the drama themselves. In this episode, we'll follow the trail from quiet calculations to world-shaking consequences, from candlelit pages in Latin read by a few hundred people, to equations that guide every GPS signal and satellite orbit. We'll see how years of patient, often frustrating work suddenly crystallize into a single line of thought that reorders entire fields, and why those rare turns in thinking still govern the way your phone, your maps, and your daily commute actually function. The strange part is how ordinary the moments around these revolutions looked. Newton was wrestling with stubborn calculations and rival theories about comets and tides. Einstein was juggling patent filings and train schedules, not lightning bolts of inspiration on mountaintops. Their Eureka points sat on top of piles of false starts, half-baked drafts, and arguments with colleagues. In this episode, we'll stay close to that messy layer. The conferences, failed experiments, and scribbled margins where a slight adjustment, sometimes a single symbol, quietly flipped the rules that engineers, navigators, and physicists still rely on. The trail to Newton's law of gravitation doesn't start in an orchard. It winds through tables of planetary positions, arguments about comets, and awkward questions no one quite knew how to pose. By the 1670s, careful observers like Tycho Brahe and calculators like Johannes Kepler had turned the sky into numbers, ellipses, periods, and empirical rules. Newton's leap was to treat those rules as shadows of something deeper, a single mathematical pole connecting cannon shots to Saturn. The inverse square idea was circulating in bits and pieces. What Newton did was weld it into a quantitative statement: double the distance, quarter the pull, the same pattern for an apple and the moon. That act of writing one compact relation and then refusing to let it go forced him to rework orbits, tides, and even the shape of Earth. Principia wasn't just a book, it was a test rig. Each proposition asked, if this law is true, does this phenomenon fall into place? Enough of them did that the scientific world, slowly, began to bet on the law. Yet those Latin pages reached only a few hundred readers. Many resisted the idea of action at a distance. Gravity, to them, sounded suspiciously like magic smuggled back into a supposedly mechanical universe. The controversy was less about equations than about what kinds of explanations felt acceptable. That tension between "it works" and "it makes sense" would surface again with Einstein. By 1905, physicists faced a different pile of mismatched pieces: electromagnetic theory, puzzling results about the speed of light, and the stubborn failures of attempts to detect Earth's motion through an ether. Einstein's special relativity didn't add a new substance, it renegotiated the rules about what must stay the same for all observers. 10 years later, general relativity went further, tying gravity to the geometry of space-time itself. Updating from Newton to Einstein is like swapping a beautifully detailed floor plan for a full 3D structural model that flexes under load. Both guide construction, but only one tells you when the building itself begins to bend. Those conceptual shifts became tools. Engineers now routinely insert relativistic corrections into satellite clocks. Astronomers treat space-time curvature as standard plumbing in their models of galaxies. The aha moments hardened into infrastructure, quietly shaping which designs are viable and which questions sound reasonable to ask at all. When those equations left dusty libraries and entered workshops, they turned into very practical questions. Naval officers asked, "How do we steer a ship across oceans with fewer wrecks?" Artillery teams asked, "How do we aim so a shell lands where charts predict, not where guesswork hopes?" Newton's mathematics quietly upgraded these tasks from craft to calculation. You could treat a cannon range table like a recipe book, plug in angle and powder, read off where the projectile should fall. Einstein's work bred its own breed of engineers. Radio technicians had to rethink how signals synchronized across long distances, then across continents. Later, spacecraft designers planning planetary flybys used those space-time bending trajectories the way expert rock climbers use tiny holds, subtle but decisive. Even movie animators now borrow relativistic effects when simulating extreme scenes, the way architects consult load diagrams before daring a bold overhang. Once an abstract insight exists, anyone with a stubborn problem can try fitting it like a new tool onto an old workbench. Future implications may feel remote, but they'll leak into daily life the way weather forecasts once did. Better space-time models could steer cargo through orbital shipping lanes and thread probes through asteroid belts. Relativity-aware clocks may anchor financial trades or secure voting systems. New detectors might turn the cosmos into a constant data stream, like a stock ticker for the universe, inviting the next generation to notice patterns today's tools can't yet see. History's next leap may start with someone debugging a simulation or tweaking a lab setup after hours. Today's cryptic data glitch could be tomorrow's new law. Your challenge this week: when something doesn't fit the rules you know, don't smooth it over. Treat it like a loose thread that might, if pulled patiently enough, unravel a whole new pattern. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!